I'm Emily Abbott from the American Chemical Society. Welcome to this media briefing from ACS Fall 2022. For many of us around the world right now, we're in the peak of summer, and those of us who are lucky enough to have access to air conditioning are thankful. Mother Nature, on the other hand, is not so pleased because of the greenhouse gases these machines have the potential to emit. During installation, maintenance, and replacement, many AC units leak the gaseous hydrofluorocarbon refrigerants. These compounds can be significantly more potent to the atmosphere than carbon dioxide. But a research team has been hard at work trying to find a less harmful refrigerant, and they have discovered a solid that can do the job. We're joined today by Dr. Jared Mason, the primary investigator of the study, and his postdoc, Dr. Adam Slavny from Harvard University, to talk more about the team's research. Thanks for joining us.
Thanks for having us.
I'm going to start with a simple question. How did you get the idea for this project?
The idea for this project really originated from some work my group was doing to try to develop materials for addressing challenges related to storing thermal energy. We were trying to develop materials that underwent phase transitions that could be used to reversibly store and release a large amount of energy. And in the process of doing this, we recognized that some of the materials we were designing underwent phase transitions that were really sensitive to pressure, meaning that the temperature at which a material transitioned from a low entropy, more ordered, to a high entropy, more disordered state changed dramatically as we apply pressure to those materials. And we realized that that made them really interesting as potential solid state refrigerants. So as materials that could be used to drive cooling cycles, much like the volatile refrigerants that are used in nearly every air conditioner refrigerator around the world to drive vapor compression cooling cycles. And driving a cooling cycle with a solid material is really hard to do because most solids that undergo phase transitions in the solid state undergo transitions that are accompanied by relatively small changes in entropy, which means not that much heat can be removed in a given cooling cycle. And those transitions can only be driven by applying really large amounts of pressure that are really impractical for a lot of cooling devices. And we realized the materials we were working with could undergo reversible phase transitions that have very high entropy changes with very small pressures. And that's what got us excited about exploring the potential for solid state cooling.
Your team, did they discover this class of barocaloric materials that you've been using, or were their refrigerant properties already known?
So the refrigerant properties were not known, but the class of materials that we initially started investigating had been known really since the 1960s or 70s. Originally investigated for some very different reasons, mostly related to magnetic and optical properties. But the thermodynamics and pressure sensitivity of the phase transitions that these materials underwent had not been studied. And their potential for cooling or for serving as solid state refrigerants had not been recognized. And so that was what my team recognized was their potential. And then that led us to synthesizing new materials in a similar class that exhibited even more promising properties for refrigeration and other cooling applications.
So the specific substance that you landed on is a metal halide perovskite. Can you explain what that is?
Yeah, sure. So metal halide perovskite is a 2D material. So it has a metal surrounded by 6 halide ions. This is something like a chloride or a bromide. And those form an octahedral shape. And each octahedron connects into a long infinite layer. And then separating each of these layers from one another is typically an organic ion. And we can put really whatever we want in those layers. But to do solid state cooling, we usually just put a very long carbon chain. So something in the range of 8 to 12 carbons. And this is important because those carbons undergo the order to disorder transition that Jared was talking about around room temperature.
Can you talk about some of the challenges associated with turning the barocaloric materials you discovered into a commercially viable cooling device?
Yeah, so we have materials that we think are pretty good. The tricky part now is figuring out a couple of engineering challenges. So these materials need to operate at about 200 bar of pressure, which is not very high as these things go, but does mean you need an entire stainless steel container for that pressure. Another important problem to be solved is how do you transmit that pressure from wherever you're generating it onto the material, and then how do you get your heat that your material is putting in and out away from the material to either side. So if you need some sort of fluid to both carry the pressure to the material and also to take the heat away from the material.
How are metal halide perovskites able to mimic a gas's ability to act as a refrigerant?
Yeah, so to answer that question, I can maybe just quickly give an overview of how existing refrigerants work. And so nearly all cooling around the world is currently provided by really the same underlying technology that relies on compressing and expanding a gaseous or volatile refrigerant, usually a fluorocarbon. And so you start with a refrigerant, gas at ambient temperature and pressure, compress it and condense it into a liquid that releases heat. That heat gets dumped to the environment to return your material back to its original temperature, but now in a lower entropy, more ordered liquid state. Then the liquid is expanded, evaporated to generate a gas that sucks up heat from the environment, can be used to remove heat from a heat source like the inside of your fridge, much like when you have sweat evaporating off of your skin, going from liquid to a gas, and that produces a cooling effect. So the two-dimensional perovskites that Adam described operate in a very similar manner in that they undergo a phase transition from a higher entropy, more disordered state, kind of like the gaseous state of a fluorocarbon refrigerant, to when they're compressed, they undergo a transition to a more ordered, compacted, lower entropy state, like the liquid state of a fluorocarbon refrigerant. And the energy and entropy changes associated with those phase transitions can allow you to take heat from where it's being generated, like in your fridge or inside a room or a warm building, and move it out to the surrounding environment. So that's how these two-dimensional perovskites can act as all solid-state refrigerants.
So I assume once this is ready for consumer use, households will have to buy a whole new system. They can't just replace the gaseous hydrofluorocarbon refrigerant that's in their current systems with a solid one. Is that right?
Probably they will have to replace it. It's still something we're trying to figure out. The biggest thing right now is that the systems we're designing are going to operate at somewhat higher pressures than existing air conditioners. And so in that case, yes, you would need to replace it. But in other ways, if we just have a fluid moving through our air conditioner in the same way that theirs is, it may be possible that you could retrofit something, but we're still trying to figure that out.
Well, thank you both for sharing your research with me today. This is really interesting stuff.
Thanks for having us.
Thanks for having us.
Be sure to check out our other media briefings for ACS Fall 2022, which will be posted throughout the meeting at www.acs.org/ACS Fall 2022 briefings.